Good day, everyone, especially to you, Sir Harris. We are pleased to present our study entitled Graph Theory-Based Analysis of Road Traffic Reduction from Bulacan State University to Robinson Highway in Malolos. I'm Kim Lesa Cortez, and together with my group, Elaine Abanes, Kathleen Julia Bagnol, Ross Jericho Espadilla, Elaine Nicole Francisco, and Alea Nicole Kimpo will be presenting this study.
For the next slide, the objective. First, apply key graph theory concept. Second, identify problem scope and alternatives. Third, implement graph-based traffic analysis. Fourth, evaluate effectiveness of solution of this problem. Lastly, support urban planning with mathematical models. Next slide.
The introduction discusses the growing issues of traffic congestion in urban areas, particularly along the route from Bulacan State University to Robinson's Place, Malolos. It emphasizes the role of graph theory in modern traffic management, where roads and intersections are modeled as edges and vertices. The paper aims to analyze and propose efficient solutions to traffic problems using graph theoretical methods such as the shortest path problem, maximum flow algorithm, and graph coloring. It also highlights prior studies demonstrating the effectiveness of these methods in optimizing roads, signal timing, and minimizing congestion. The researchers plan to replicate and adapt these strategies to the local context of Malolos, Bulacan by mapping the traffic network and suggesting improvements for better traffic flow and reduced travel time. Graph theory is a branch of mathematics that studies graphs, structures made up of vertices connected by edges, with the goal of understanding their structures and solving problems related to connectivity, pathfinding, and network optimization across various fields. Analyzing traffic congestion on Bulsu to Robinson-Malolos Highway can analyze the congestion and suggest a solution, as graph theory has been effective for modeling networks such analyzing the road system, traffic flow, and intersections. Intersections and roads connecting them are modeled as vertices and edges. Pathfinding and connectivity are essential for determining and analyzing traffic flow, movement, and reducing traffic congestion.
For the next topic under preliminary, the concept and problems in graph theory. This explains that studies the relationship between objects using nodes or the vertices and the connection or the edges. It is widely used to model real-world systems like social networks, transportation routes, and even chemical structures. By representing objects and their relationship as graphs, complex networks become easier to analyze and optimize. For the next slide, the shortest path algorithm. It uses weighted edges to represent travel time or distance and can incorporate real-time traffic data for dynamic routing. Algorithms like Distrust and Bellman-Ford help to compute the shortest path depending on whether the traffic conditions are static or changing. For the last slide of the preliminary, the maximum flow algorithm. In this model, nodes represent intersection and edges represent road segments, each with a defined capacity, the maximum number of vehicles it can handle. In traffic control seeks to determine the most efficient way to route vehicles through a network without exceeding road capacities. Next slide.
Now, let's focus on one of the most critical areas of traffic congestion in our study, the T intersection near Bulacan State University, Gate 1, where MacArthur Highway meets Catmon Road. This intersection is a common choke point, especially during rush hours, when students and local commuters travel to and from Bulacan State University. Traffic builds up in this area often leads to delay, stress, and reduced productivity. To analyze this, we converted the road layout into a directed graph, which helped us represent and understand the flow of traffic in mathematical terms. In our directed graph, nodes or vertices represent key stopping or transition points at the intersection. This includes A2, B1, and C1 as source nodes, the points where vehicles enter the intersection, while A1, B2, and C2 as sink nodes, the exit points. Edges represents possible directions of vehicle movement, for instance, from A2 to C2 or B1 to B2. Each direction was analyzed to understand which flows are possible under different traffic light phases or manual traffic enforcement. For example, when vehicles from C1 to A1 and B1 to B2 are stopped, those from A2 to B2, A2 to C2, C1 to C2, and B1 to A1 are allowed to move. This pattern changes cyclically to ensure every direction gets flow time, but it's not always efficient. Despite traffic pacing, congestion occurs because of bottlenecks, parts of the network where flow capacity is lower than the demand. Using the maximum flow algorithm, we found that the main bottleneck edges are E2 to C2 and C1 to A1. These road segments have limited capacity compared to the volume of vehicles trying to pass, especially from the student-heavy routes like Katmon Road. According to maximum flow analysis, traffic builds up when the inflow of vehicles from source nodes, which is A2, B1, and C1, exceeds the capacity of sink nodes of A1, B2, and C2. This mismatch leads to congestions and delays. To address this, we apply the shortest path algorithm to propose a detour route that avoids the T intersection altogether. We create a weighted directed graph comparing two routes. Path A, the original route that passes through the T intersection. Path B, an alternative route that bypasses it. Here's what we found. Path A, through the intersection, measures 1,120 meters, while in Path B, the alternative route, only measures 748 meters. Well, that's 33% shorter in distance. Therefore, rerouting vehicles from east to the south using the alternative road can significantly reduce the congestion at the intersection.
Now, proceeding to the second part of the main discussion, the Malolos Crossing flyover. But first, it is important to note that flyovers are elevated roadways that helps manage the traffic flow by dividing the number of vehicles that passes through the same intersection. The aim of this discussion is to analyze the purpose of the Malolos Crossing flyover to the management of traffic flow in Malolos, Bulacan by the use of the shortest path problem or maximum flow problem in graph theory. Transforming the map into a graphical theory problem, we have acquired 8 vertices and 12 edges directed graph. Applying the shortest path problem to identify the fastest route to arrive at certain vertices in Malolos Crossing flyover. So we have an example of trying to arrive from vertex 1 to vertex 4. We have acquired two possible routes that leads to the vertex 3. So the first route is from vertex 1 to 8, 8 to 4, and by getting the sum of the distance that can be seen in the graph, we will have a total sum of 210 meters. Now if we try to start from the vertex 1 straight from vertex 4, we will have a total distance of 130 meters. This explains how starting from the roads of Paseo de Congreso Street to the other side of Malolos Crossing is much more efficient than the other route. And the last example is trying to arrive at vertex 3 at any given point, but then if we also try to start at the same point, we will have a route starting from 1 to 8, 8 to 4, and 4 to 3, which will have a total of 370 meters of distance, while if you try to take the route from 1 to 4 and 4 to 3, you will have a total of 210 meter of distance, which means that you do not need to arrive at vertex 8 in order to arrive at vertex 3. So this explains how the shortest problem helps us to be efficient, especially when calculating the distance of our routes. So this short analysis proves that the shortest path problem can be applied in the intersection roads of Malolos Crossing. Now proceeding to the analysis of how the crossing flyover is important to that intersection road in Malolos, by removing the vertex and edges that connects or represent the crossing flyover, in here you will already notice the possible scenario that could happen if there was no Malolos Crossing flyover above the said intersection. We need to know that now that the flyover was removed, the total number of vehicles will be doubled, which means more traffic congestions and longer travel time. It will be much more noticeable if we had a data for how many vehicles are passing through the intersection of Malolos. But even so, with a simple graph, we can notice the huge difference that a flyover would make in terms of traffic flow management. In here, we will realize that by application of the shortest path problem and maximum flow, we were able to notice how the Malolos crossing flyover plays a huge role in the Malolos intersection to prevent the traffic congestion and by efficiently managing the numbers of vehicles that passes through the MacArthur Highway from the Robinson Malolos to Bulacan State University. Now proceeding to the last section of this discussion, it will tackle the intersections in the Robinson's Malolos.
Robinson Malolos, located along MacArthur Highway in Malolos City, Bulacan, was modeled using a directed graph with 6 vertices and 5 edges to represent mall entrances, exits, and connecting road segments. Each vertex represents a key location, and each edge represents a possible path vehicles can travel, weighted by the distance in meters. Maximum flow algorithm was applied to determine the optimal paths vehicles can take from Bulacan State University to the mall, specifically from vertex 1 or the entrance, or vertex 2 or the side approach, to vertex 6 or the exit. This analysis helps identify conjunction points, suggests alternative routes to ease traffic, and aids in future traffic and lane capacity planning based on flow limits like the 3.42 meter minimum capacity between certain nodes.
For the summary, for the first bullet, the study focused on reducing traffic congestion from Bulacan State University to Robinson Highway by applying graph theory models. This indicates that it used graph theory as a framework to model and analyze the traffic flow within this urban corridor. By treating roads and intersection as a network of nodes and edges, the study provided a structured approach to understanding and improving traffic movement. For the second bullet, it utilized the shortest path problem and maximum flow algorithm to analyze key congested areas like the T intersection, Malolos Crossing, Flyover, and Robinson Place, Malolos. This indicates that the research applied the shortest path problem to identify quicker, less congested routes for vehicles. It also used the maximum flow algorithm to determine the capacity limits of key road segments. These methods were applied specifically to high traffic areas such as the T intersection near BSU Malolos, Malolos Crossing Flyover, and Robinson's Place Malolos. Lastly, the results highlight that congestion occurs when inflow exceeds road capacity and propose solutions like alternative routing and optimized traffic signal coordination to improve flow. This indicates that the study proposed redirecting vehicles through alternative routes with shorter travel time. Additionally, it recommends optimizing traffic signal timing to improve the overflow of vehicles in congested zones or area.
To conclude, this research underscores the power of mathematics, particularly graph theory, in solving real-world urban issues like traffic congestion by focusing on the route from Bulacan State University to Robinson Highway and evaluating critical intersections such as T intersection at Gulso and the Malolos Crossing flyover. We were able to uncover how traffic volume shapes congestion patterns, and more importantly, how these patterns can be addressed using strategic, mathematically based solutions. The use of maximum flow algorithms and shortest path problems allowed us to correctly identify nearly all traffic bottlenecks and to suggest practical, evidence-based methods for improving the overall traffic flow. These techniques provide a systematic and data-driven approach to managing congestion. Our findings go beyond this specific case study. They serve as guideline for urban planners and policymakers, showing how mathematical models can inform smarter traffic policies that promote smoother, faster, and safer travel. As cities continue to grow and face increasing transportation demands, it becomes more essential than ever to adopt innovative and sustainable solutions. Graph theory offers exactly that, a means to enhance mobility, reduce environmental stress, and build more efficient and livable urban spaces. Ultimately, this study proves that cities truly thrive when they embrace mathematical modeling as a core element of traffic management and urban development.